Okay, in this video we are going to look into some definitions, and with the help of that definitions we are going to prove some lemma. Okay, first of all, what is the definition we are going to see is automorphism of the field K. I already defined this definition in the previous video for proving the theorem. Now I am restating it. By an automorphism of the field K, we mean a mapping sigma of K onto itself such that it satisfies these two conditions. I can explain this definition in such a way that if sigma, we can say sigma is an automorphism if it maps the field K, if it maps the field K into itself and it satisfies the two properties. What are all the properties? Like it, I can say that it just preserves the operation, right? Because if I take a plus b addition and then take sigma, also if I take sigma and then add, both are same, which means I can say that it preserves the operation, right? So a mapping which preserves the operation and it maps the field into itself is called an automorphism of the field K. That is the definition. Now I can say some remark. Two automorphisms sigma and tau of K are said to be distinct if sigma of A not equal to tau of A for some element A in K. If there exists an element A in K such that that element mapping under sigma and tau are not same, then I can say that these two automorphisms are different. This is just a small remark which we already used in the previous theorem, right? Now we are going to see what is the definition of a fixed field of a group. Okay, if G is a group of automorphisms of K, I am considering that G is some group of automorphisms of K. Okay, then the fixed field of G is the set of all elements A belongs to K such that sigma of A equal to A for all sigma belongs to G. What they are saying is that if G is the group of automorphisms of K, then they are saying fixed field of G is the set of all elements of K such that for all automorphisms on G, if I put that element into that automorphism, I'll get it same. I'll get the same element back even if I apply that automorphism. Like for explaining purpose, if I take G to be equal to sigma 1, sigma 2, sigma n, the set of automorphisms of K. I'm just telling you for explaining the definition. Okay, this is not true. I'm just trying to convey the definition. If I take G is equal to sigma 1, sigma 2, sigma n, I can say the fixed field of G will contain A if sigma 1 of A equals A, sigma 2 of A equals A, also etc. sigma n of A equals A. That is, for all the automorphisms of G, automorphisms of K, if I put that element into it, I'll get the same element back. Those elements contribute the fixed field of G. Okay. Now we are going to prove that the fixed field of G is a subfield of K. Do you know what is meant by a subfield of K? It is nothing but a field which is contained in K, right? Okay. Now we are going to prove that the fixed field of G is a subfield of K. Let G be the group of automorphisms of K. Okay. Let us denote the fixed field of G by H. We are just denoting the fixed field of G by H. We already know the definition of fixed field, right? It is the collection of elements which when applied when applied by the automorphism will get the same element back. So those collection will contribute the fixed field of J. Now I am going to prove H is a subfield of K. That is what I have to prove, is that H is contained in K and H itself is a field. Despite of proving that, we have some result. To prove something is a subfield or something, we can prove like A plus or minus B is in H, and also we have to prove that AB inverse belongs to H. That is, I'm proving that it is a subgroup under addition and it is a subgroup under multiplication. If I prove that two things, I can very well say that it is a subfield. Okay, this is some result I have studied before. Okay, but for proving that, we are taking some A and B from H. If I take some A and B from H, what are the properties it has? Sigma of A equals A and sigma of B equals B. This is true for all sigma belongs to G, right? Now, if I consider sigma of A plus or minus B, I can spread it out because sigma is an automorphism of the field and it has the property of preserving the operation. So I can spread it out, sigma of A plus or minus sigma of B. I know that sigma of A equals A. Why? Because A is an element of H. H is the fixed field of G. So I will get A plus or minus B. And then sigma of AB equals what? Sigma of A into sigma of B. But I know that sigma of A is A and sigma of B is B. So, okay. If I spread sigma into sigma of A plus or minus sigma of B, I will get A plus or minus B, and sigma of AB is equal to sigma of A into sigma of B, which is nothing but AB. So what I get is A plus or minus B and AB belongs to H. Now I am going to prove that B inverse belongs to H. If B not equal to 0, then we have sigma of B inverse equals sigma of B the whole inverse. Okay. Then sigma of B the whole inverse is not, I know that sigma of B equals B. So sigma of B the whole inverse is nothing but B inverse. So I can very well say that B inverse belongs to H. Thus with the help of this I can say that H is the subfield of K, right? Why? Because B inverse belongs to H and AB belongs to H. A plus or minus B also belongs to H. So with the help of these things, I say that H is a subfield of K. Now we are going to see a definition. Let K be a field and F be a subfield of K. K is the biggest field and F is its subfield. Then the group of automorphisms of K relative to F written by G of K comma F is the set of all automorphisms of K, leaving every element of F fixed. Okay. G of K comma F is nothing but the set of automorphisms of K, leaving every element of F fixed. Which means what? Leaving every element of F fixed means what? If I put an element of F over under that automorphism of K, I'll get the same element back. Okay, what is the difference between this definition and the fixed field of a group definition? In the fixed field of a group, we collect the elements of F. Okay, actually the elements of K. We collect the elements of K which we put under an automorphism of K, will get the same element back. But here we are collecting the set of all automorphisms which fix every element of F. Okay, so G of K comma F, the automorphism sigma of K is since G of K comma F if and only if sigma of alpha equal to alpha for all alpha belongs to F. There we have sigma of A equals A for all sigma belongs to G. Here we have sigma of alpha equal to alpha for all alpha belongs to F. Okay. Okay, now I am going to prove that G of K comma F is a subgroup of the group of all automorphisms of K.